हेलो मेरे प्यारे बच्चों, वेलकम टू द चैनल डियर मैथ्स. So today we are going to learn about the real numbers and their decimal expansion. So as we have studied that real numbers comprises of rational numbers and irrational numbers. So these are the combinations of both rational numbers and irrational numbers. So first we will learn about the decimal expansion of rational numbers. So here we will understand by taking down three different examples. So let's say find the decimal expansions of is it 10 by 3, 7 by 8 and 1 by 7. So we will look at the decimal expansions of these numbers one by one. So let's take the first decimal number as 10 by 3. So we will divide 10 by 3. So here we will see 3 3 is 9. So remainder is 1. So we will put decimal here. So there is again 3 3 is 9. Again decimal 1. Again we'll extend 3 3 is 9. Again remainder 1. 3 3 is 9 and so on. So again that remainder. Second example is like 7 by 8. So we are going to divide 7 by number 8. Here becomes 0. We will put the decimal. So here becomes 8 8 is 64. So here minus. So here remainder is the 6. Again 8 7 are 56. 4 8 5 are 40. So here the remainder is 0. So here the digit. So next one is the third example is 1 by 7. So we will divide the 1 by 7. Again 0. So we will put the decimal. So again 1 7 1 is 7. Here remainder is 3. So again 7 4 is 28. So remainder is 2. Again 7 2 is 14. Decimal remainder is 6. So again 7 8 is 56. 4 7 5 is 35. So again remember 5. 7 7 is 49. Again remainder 1. So here the remainder is again 1. So here it starts to repeat. It will start to repeat. So here we can say in this case, in the first case, the remainders are in the first case remainders are 1 1 1 and 1 1 1 1 1 and so on. In the second case, remainders are 6 4 and 0 6 4 0. And in the third case, remainders are 3 2 6 4 3 2 6 4 5 and 1. So again it will repeat like 3 2 6 4 5 1. So here we are noticing the few patterns. So here we can say these patterns are not only limited to the above examples. It is true for all the rationals, that is p by q where q is not equal to 0. So here we can say, if we take the example 2, here we can say, so the it is terminating. So there is at certain step there is not any remainder. So we can say that its expansion is terminating, and if we take the example first and third, so we can say after certain steps, the remainders are repeating or recurring. So on this basis, we can take the two conditions. The one can be like the remainder becomes when the remainder becomes zero, and the other conditions when the remainder never becomes zero or it is recurring. So let's take the first condition when the remainder becomes zero. Let's take case 1 when becomes 0. As we have seen in the second example, the remainder becomes 0 after some steps, and the decimal expansion is, so if we see in the second example, here the decimal expansion is like 0.875, so we can say its decimal expansion is 0.875. So other examples, we can also take some other examples, and other examples are like 1 by 2. If we take 1 by 2, its decimal expansion is like 0.5. 1 by 4, its decimal expansion will become like 0.25. Like next another example like 31 by 25, its decimal expansion is like 1.24. If we take another example like 3 by 5, its decimal expansion is 0.6, etc. So here all the remainders are 0 at certain steps. So we can say in all these cases the decimal expansion terminates after a finite number of steps. So when the decimal expansion ends or terminates, then it is called as the terminating terminating decimal expansion. So we also notice that when the denominator is the power of 2 and 5, it will always be terminating. Excellent. See, he can say like 2, 4, 25, 5, 125, 16, 32. All are these the at power of if the denominator in these terms. It's uh, they will always terminate. So these will call the terminating decimal expansion. So here let's take another case when the remainder never becomes 0. So as we can see in the case 1 and 3 examples above, the remainders repeat after a certain stage, forcing the expansion to go forever, or the quotient repeats, making a repeating block of digits. So this expansion is referred as a non-terminating recurring decimal expansion. So here we have seen the 10 by 3 was equal to the like 3.3333 and so on. So we can say here the 3 is repeating, so we can write it like 3. So it is making a block of 3. So we can repeat it as the like 3.3. So here the 3 is repeating. Another one was like 1 by 7. So 1 by 7 was like 0.142857, and it is again repeating like 142857 and so on. So here we can say like So here this is a block, repeating block, where we can write this as in this form. So we can say when the decimal expansion is terminating or non-terminating recurring, it will always are rational numbers, right? So with these two cases, we can conclude that if the whether the decimal expansion is terminating or non-terminating recurring, it will always are rational numbers. So now let's take the case of irrational numbers. So we have seen in case of rational numbers that the decimal expansion of rational numbers is either terminating or non-terminating recurring. So in the case of these irrational numbers, the decimal expansion of an irrational number is non-terminating and non-recurring, means its decimal expansion after a certain step, the digits will not repeat. So we can also say if a number whose decimal expansion is non-terminating, non-recurring will be a irrational number. So now let's take an example. So the decimal expansion of few irrational number like square root 2 and pi r. So square root of 2, the decimal expansion will be like 1.41421356237048 and so on. So here we can see it's none of the digits is repeating. Similarly, the decimal expansion of pi is equal to the 3.14159265358979 and so on. We often take the value of pi as 22 by 7 as an approximate value, but but this pi is never equal to the 22 by 7. So that's why we consider it as an irrational number. So let's find an irrational number between two rational numbers, that is 1 by 7 and 2 by 7. So earlier we have calculated the rational number between two rational numbers, but now we are going to calculate the irrational number between two rational numbers. As we know that the decimal expansion of 1 by 7 is equal to the 0.142857 and it is repeating, right? So similarly we can also write it as like 2 by 7 is equal to the 2 times of 1 by 7, like it will become like 0.285714 and so on. So it will repeat. So since the irrational number is non-terminating and non-recurring, we know that the irrational number are non-terminating, non-recurring. So hence we can find infinitely many such numbers between 1 by 7 and 2 by 7. So one such numbers can be like 0.15, 015, 0015, 00015 and so on. Another number can be like 0.16, 016, 0016, 00016 and so on. So now let us solve few examples like show that the number 3.142678 is a rational number. In other words, express the 3.1426 in the form of p by q, where p and q are integers and q is not equal to 0. So since this is a terminating number and can also be written in the form 3.142678 divided by 1. When we will cancel out this decimal 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 0. So on simplification, you can also write it as like 1, 5, 7, 1, 3, 3 and 9. Let's divide by 5, 1, 2, 3, 4 and 5. And this is a rational number. So next question can be like show that 2.3333 can be expressed in the form p by q, where p and q are the integers and q is not equal to 0. So let us assume that x is equal to the given number, that is 2.3333. See, since one number is repeating, okay, here is the block of one number, so we will multiply on both sides the equation by 10. Since single digit is repeating, and multiplying 10 on both sides. So we will get 10 times of x equal to the 10 times of 2.3333. So that is equal to the 23.3333. So that is the 10x. We can also write it like 10x is equal to the 21 plus 2.3333. So here we can see like 2.33 from equation 1, this value is equal to the x. So we will substitute this value. So like it will become 10x is equal to the 21 plus x. So if you bring x to the left hand side, so it will become 9x equal to the 21. This implies that x equal to the 21 divided by 9, and we will simplify here x equal to the 7 by 3. So, the digit 2.333 becomes the digit 7 by 3. That is the rational number. We can also verify by reverse. So by reversing, when we divide 7 by 3, like 3 to the 6, here it becomes 1. So we will say decimal 0. So 3 3 is the 9, again 1, it will become 3 3 is the 9, again 1, it will become 3 3 is the 9, again, and so on. So this will be equivalent to 2 3 3 3 3 3. So the same answer. Here let's solve another example. Here two digits are repeating. Let's show that 1.2929 can be expressed in the form of p by q. Let's solve this problem. Again, we will consider x equals to the 1.2929. Question number 1. So since two digits are repeating, so now we will multiply by 100 on both sides of the equation. So like 100 into x equal to the 100 into 1.292929. It will becomes like 100 x is equals to the 129.2929. It will become, we can also write it like 128 plus 1.2929. So here again we can see from equation 1 this value is x. We will substitute this value. It will become 100 of x equals to the 128 plus x. When we bring x on the left side, it will become like 99 times of x is equal to the 128. So hence x is equal to the 128 by 99. So here this is a rational number. So we can also verify it in the reverse process, like divide the 128 by 99. So we will get like 1.29299. So here 1.29 can be expressed in the form of p by q. That is the 128 divided by 99. So there is one more example. So that 0.235335 can be expressed in the form p by q, where p and q are integers and q is not constant. Here after one digits are repeating. So here again we will consider like x is equal to the given number 0.23535. Consider it as equation number 1. So since again two digits are repeating, we will multiply 100 times on the both sides of equations. It will become like 100 x is equal to the 100 times of 0.2353535. Here it will become like 100 times of x is equal to the 23.533535. Again, we can also break this equation, which equal to the 23.3 plus 0.23, 0.2353535. Again, from equation number 1, we can see this is the value of x. So on substituting, we will get 100 times of x is equal to the 23.3 plus x. On bringing the x to the left side, we will get 99 times of x is equal to the 23.3. So here x will become 23.3 by 99. So we can cancel out the decimal. So here x will become 233 by 993. This is again a rational number.